All right. Can everyone see the slides?
Yes.
Okay. Yeah, I'm Timothy Farkas. I'll talk about auto-scaling at Netflix. So what was the problem we had? Well, at Netflix, we have a service called Keystone, and Keystone runs several thousand Flink jobs called routers. These routers are simple Flink jobs with a single source and single sink. They consume from Kafka, do a projection or filter, and then write out to a sink, which could be an Elasticsearch cluster or another Kafka topic or an iceberg table. So originally, we were manually scaling these routers as they were running in production to handle changes in incoming traffic. So we had alerts set up for all the routers, and if a lag threshold was exceeded for a router, we would get a page and we'd have to go in and manually scale up the cluster. So this was not very pleasant, running several thousand of these jobs. We would get several pages a day at all times of the day and night, and we would just have to manually scale these things up. And we also ended up severely over provisioning the jobs. So we wanted to automate this. So we implemented auto scaling. This is the high level auto scaling architecture. So the Flink jobs, the routers, run in our container platform called Titus, and the routers publish metrics to Atlas, which is our metric aggregation platform at Netflix. The autoscaler would then consume these Atlas metrics and make scaling decisions. Once the autoscaler makes a scaling decision, if it wants to resize a router, it would invoke the Flink control plane, which would then delegate the request to Spinnaker, our cluster management layer, which would then talk to Titus to add or remove nodes from a particular router cluster. So within the autoscaler itself, there are several steps happening. The first step is just simple metric collection. Then we apply a pre-decision policy. Then we decide whether to scale up or down or keep the cluster the same. After we make a decision, we calculate how much to scale up or down by. Then we apply a post-decision policy, and then we initiate a rescale action. So I'll go into each of these steps in more detail. So for metric collection, metrics are published once a minute. So for each router, every minute, we batch the metrics for that router together. And some of the metrics we look at are Kafka consumer lag, processing rate per second of the router, CPU and network utilization, the incoming event rate on the Kafka topic, and health metrics for the sync cluster. So after we have our batch of metrics for a given router at a given minute, we apply the pre-decision policy. So the pre-decision policies decide whether or not auto-scaling should be aborted, because in certain cases, it doesn't make any sense to take an auto-scaling action. So for example, if the Flink job is having task failures or checkpoints are failing, or the sync cluster the router is writing to is not healthy, then it doesn't make sense to take any auto-scaling action in those cases. Also, similarly, if the router is in the middle of a redeploy operation, it doesn't make sense to auto-scale then. So if any of those situations happen, auto-scaling is aborted. But if none of those exceptional cases happen, we move on to deciding whether to scale up, scale down, or keep the cluster the same. So the criteria to scale up is pretty simple. We scale up if there is significant lag for the router, or if resource utilization of the router exceeds a safe threshold. So there's an important piece of information here. When we decide to scale up, we're essentially saying that the cluster, the router at its current size is processing events at its maximum throughput. So when we make a scale up decision, we essentially have a mini benchmark for the performance of the router at that current cluster size. So whenever we make a scale up decision, we save the performance of the router at that cluster size in a performance table to make future scaling decisions. And I'll talk more about that performance table later. The criteria to scale down is also simple. So if the router has no lag and we don't anticipate an increase in incoming messages, and a smaller cluster size can handle the current event rate, then we'll scale down. Now, there are some more details here, like how do we anticipate if the incoming event rate will increase? There's some work to be done to do that, and I'll talk about that in the predict workload section. Similarly, how do we know if a smaller cluster size can handle the current event rate? That's covered in the performance table section later. So if we don't meet the criteria to scale up or scale down, then we keep the cluster the same size. But if we decide to scale up or scale down, then we move on to calculating how much to scale up or scale down by. So this is the calculate size step. So when calculating the new desired cluster size, there are 3 more steps to do that. The first step is to predict the future workload by fitting a regression function to the historical incoming event rate for the source topic and using that regression function to predict what the future event rate for the source topic will be. Once we have that regression function, we need to compute the target event rate for the router required for the router to keep up with its backlog and traffic. After we compute the target event rate for the router, we can do a cluster size lookup by using the target event rate to look up in the performance table a cluster size that can handle that target event rate. So I'll go into more detail for each of these. So for predicting workload, we do that by fitting a regression function to historical data. So in the graph on the screen, this is a graph of the event rate for a source Kafka topic over time. The arrows point to just a given point in time. The blue areas of the graph represent historical event rate data that we use to compute a regression function at a given point in time. And the red area represents the regression function's prediction for the future event rate after a given point in time. So for smooth workloads, this works pretty well. You can use historical data to pretty accurately predict what the workload will do in the near future. But there are cases where this breaks down. So in production workloads, sometimes the traffic can be spiky. Maybe the traffic follows a smooth sinusoidal pattern most of the time, but then there's a sudden spike because something changed in production. These spikes, if they're handled naively when computing your regression function, they can make your regression function really inaccurate. So you need a way to handle them to make sure that even in the case of spikes in the incoming event rate, our regression function can still be accurate. So we do this by assuming that a good regression function has an error in its predictions that is normally distributed and centered at 0. We find the historical error of the regression function, and we take the standard deviation of the historical errors. Then we say that if we encounter, for any prediction that the regression function makes, if the error of that prediction is greater than 3 standard deviations of the historical error, we call that new data point an outlier. And if we observe enough consecutive outliers, then we need to reset the data that we're using to compute our regression function so that it can be more accurate. So I'll go through this in a bit more detail. So here we have a graph where the y-axis is the event rate for a source topic and the x-axis is time. We have 6 observed data points for the incoming event rate for the topic, and the blue line represents a regression function we fit to those data points. Now, if we observe a new data point at time 6, you can see that the regression function we originally computed is not very accurate. The new data point we observe at time 6 is much larger than what the regression function predicted. So it's an outlier. And then at times 7 and 8, again, we observe more outliers. The regression function predicted a much lower event rate for times 6, 7, and 8 than what was actually observed. So since this happened three times in a row, we know that something has changed with the workload, and we need to reset our baseline and recompute our regression function using the outliers and throw out all the other historical data we were using to compute the regression function. So now we have a way to predict the future incoming event rate in the source topic for a router, now through the use of a regression function. Now we need to use that regression function to compute the target throughput rate for the router. So in order to do this, we need to define 3 time periods during a rescale operation. The first time period is the restart time. So when you do a rescale, you may have to stop processing on the job for a short period of time and then restart it. So that's the restart time. Then there's the catch-up time, which is the amount of time we want it to take for the router to fully catch up with its backlog of events after a rescale action has been taken. Then there's the valid time, which is the amount of time we want a rescaling decision to be valid for. So when we compute a new cluster size and do a rescale, we don't want that to be good for only like 1 minute and then rescale again a minute later and just keep resizing the cluster every minute. We want a rescale action to be valid for a good amount of time, like 20, 30, 40 minutes. So that's what the valid time represents. Now we can compute the target event rate by first computing the total number of events by using our regression function and these time periods we've defined. So the total number of events that we're interested in is the number of events that the router will need to process over the restart time and catch-up time. So that is just the number of buffered events in the Kafka topic at the beginning of a rescale action, plus the integral of our regression function over the restart time and catch-up time. So adding those 2 things together will give us the total number of events that a router will have to process over the course of the restart time and catch-up time. Then we can compute the recovery rate, which is just the total number of events divided by the catch-up time. And then we can also compute a workload rate, which is just the predicted incoming event rate of the source topic by the end of the valid time. So then our target throughput rate for our router needs to be the maximum of the recovery rate and the workload rate. So now we have computed a target event rate for our router that needs to be rescaled. Now we need to use that target event rate to look up an appropriate cluster size that can handle that event rate. So we do that by using the performance table. So previously, I mentioned that during a scale up, when we decide to scale up, we save the current size and throughput of the cluster in a performance table, because when we decide to scale up, that means that the router is operating at maximum capacity. It's a benchmark for the throughput of the router at that current cluster size. So that's really useful information that we can reuse for computing cluster sizes later through the performance table. So I'll give an example of how this is done. So here we have a simple performance table for a particular router and a target event rate for that router. In the performance table, we can see that the router at 4 nodes was able to process 10,000 events per second. The router at 10 nodes was able to process 20,000 events per second, and so on. And we can see that the target rate we want the router to be able to handle is 15,000, and 15,000 is in between 10,000 and 20,000, which in the performance table. So we can do linear interpolation on the cluster sizes and compute a cluster size of 7. So that means a 7-node router will be able to handle the target event rate of 15,000. So that was a happy case where the target event rate was in between 2 existing entries in the performance table, but that won't always be the case, especially before the performance table has been fully populated. So here's an example where the target event rate is 40,000, which is larger than the largest entry in our performance table. So in this case, we can compute the desired cluster size by taking the largest entry in the performance table, which is 35,000, and computing the per node throughput, which is 35,000 divided by 18. And then we can compute the desired cluster size for a target event rate of 40,000 by dividing 40,000 by the throughput per node, which should give us a cluster size of 20.57, which, we can't have half a node, so we round that up and we get a cluster size of 21, which should be able to handle 40,000 events per second. So these were some simple examples to demonstrate the idea of the performance table. In practice, there are a few more corner cases. Also, you need some additional information on top of the cluster size and throughput at that cluster size in the performance table. You also need to track the resource utilization at that cluster size. Because if you need to rescale your router and you pick a new cluster size, you don't want to pick a cluster size where the resource utilization will be like 95%. You want a healthier resource utilization of maybe 70 or 80%. So you need to track resource utilization within the performance table as well. But I won't go into those details now. So one thing you may have noticed about calculating the cluster size is that I didn't distinguish between scale up or scale down. That's because the process is pretty much the same in both cases. There are a few corner cases that are handled differently between scale up and scale down, but in both cases, you need to fit a regression function, compute the target event rate, and look up a cluster size in the performance table. The process is the same. So now that we've calculated a new cluster size for our router, we need to go through the post-decision policies. So the post-decision policies provide some guardrails. So it enforces a minimum cluster size because we don't want to scale down clusters so much that a single Kafka consumer has too many partitions to handle. Similarly, we have guardrails for the maximum cluster size because it doesn't make sense to scale up the cluster so big that the parallelism of the cluster is greater than the number of partitions in the source topic. So a maximum size is enforced there. Also, we have cooldown periods for scale ups and scale downs because we don't want to be scaling up and down every minute. We want scaling decisions to be good for 20, 30, 40 minutes. So we don't allow rescale actions within the cooldown period. Also, we disable scale downs during region failovers, which I'll talk about in more detail at the end. And we have a few other safety limits, like limits on the total number of new nodes that can be added on a scale up, because we don't want to have like a rogue scale up action that adds way too many nodes. And we also have some general absolute safety limits for the maximum cluster size, because in the past we've observed that the Flink job manager can become unstable with too many task slots. So we have some hard limits on all the cluster sizes there. So after we pass through the post-decision policies, we're ready to initiate a rescale action and call the control plane to resize a cluster. So that's the high level design and flow of autoscaling. So I'll go through some results. So here's a test done with a test router and synthetic data. In the top graph, the gray area represents the event rate per second over time. So the event rate per second for the source topic. So the event rate per second over time for the source topic follows a sinusoidal pattern. And if you look at the graph below, which is of the number of nodes in the cluster, you can see that autoscaling adds and removes nodes that follow the sinusoidal traffic pattern. Now here's another slightly more sophisticated test where we have the event rate on the source topic linearly increasing over time with large spikes of 4 million events per second periodically. So you can see in the graph below with of the number of nodes in the cluster that when we encounter a large traffic spike, we allocate a large number of nodes to handle it. And when the spike goes away, we release those nodes. And every time we release the nodes after a spike, we're still following the linearly increasing overall traffic pattern. So that was just test data. Here's an example of a production router. So the top graph again is the event rate of the source topic over time. And you can see it follows a sinusoidal pattern. In the bottom graph, you can see that nodes are being added and removed from the cluster following the source traffic. So autoscaling works pretty well in production. Now here are some graphs of the aggregate resource usage of all our routers in a particular region. So the top graph is the number of nodes across all our routers in US East 1, and the bottom graph is of all of the CPU cores across all our routers in US East 1. So you can see that it follows a sinusoidal pattern with the daily ups and downs of Netlfix traffic. During high load periods, we add more nodes. During low load periods, we remove nodes. And here's the same thing, except for the EU West 1 region. So in EU West 1, you can see that we, over the course of a day, we add and remove 1,000 nodes, and we add and remove around 10,000 CPU cores, corresponding with the peaks and troughs of traffic. So some other stats are we have over 6,000 routers running in all regions and environments. Their cluster sizes can vary from 1 container to over 100, and containers can have 1 CPU to 8 CPUs. And over the course of a day, we make 1,700 auto-scaling actions. So yeah, that covers most of auto-scaling. There are some additional little things to consider when rolling out into production. There are actually many additional things to consider, but here are a few of them. So you have to think about memory requirements. Direct memory needs to be preserved for the Kafka consumer and Kafka producer. So you have to make sure to configure an appropriate amount of direct memory. A catch is you can't change the direct memory for a task manager after it's been deployed. So you have to decide the amount of direct memory you need at deployment time. And another catch is that smaller clusters actually require more direct memory for the Kafka consumer because each node handles more partitions, and larger clusters require less memory for the Kafka, less direct memory for the Kafka consumer because each consumer handles fewer partitions. So at deployment time, you need to compute what the minimum allowed cluster size will be for a router, and you need to configure a direct memory configuration that will work for that minimum cluster size. So another thing to consider is the balancing of partitions across task managers. So the Kafka consumer, when it gets assigned partitions, does a pretty good job of balancing partitions. The number of partitions assigned to the difference in partitions assigned to any 2 Kafka consumers will never be greater than 1 because they're evenly distributed across the consumers. But for Flink task managers, that's not necessarily the case because the partition assignment to the consumers is not task manager aware. So you can end up in a situation where one task manager can have significantly more partitions than any other task manager. So here's an example with 3 task managers. Each task manager has 2 task slots, and we have a topic with 8 partitions. So 4 consumers get 1 partition each, and 2 consumers get 2 partitions each. And we can get unlucky and have the 2 consumers with 2 partitions each assigned to the same task manager. So that task manager effectively has double the number of partitions to handle. So one way to handle this is to restrict the partition count for the source topic to always be a multiple of the Flink job parallelism, but that really restricts the number of possible sizes you can have for the cluster, and also the number of possible partitions you can assign to the topic. So we have a looser restriction with auto-scaling. When we make a scale-up decision, we scale up the cluster size such that the number of partitions assigned to each consumer will be reduced by 1 at least. So that's a looser requirement, but it can address some of the skew that can happen, and gives us more flexibility with partition counts and cluster sizes. So I think I have 1 more minute. So another thing is outlier containers. So all containers are not created equal. Some containers can have issues which cause them to still run, but just run slowly. So in the graph above, we have the gray area, which is the event rate for the source topic over time. The green line is the consumption rate of the router over time. And you can see that the green line is slightly below the incoming event rate. And the red line is Kafka consumer lag. So the Kafka consumer lag is steadily increasing over time. And we're just barely not keeping up with traffic. And the reason why is one of the nodes in this particular router had much higher CPU utilization because it was experiencing a lot of memory read errors because the memory in that node was degraded. So these are like some of the things you run into, and you have to be able to detect these kinds of corner cases to keep your the auto scaling algorithm from doing something crazy. Yeah, one more thing to talk about real quickly is region failover. So at Netlfix, we publish data. We have traffic running in 3 regions: EU West, US East, and US West. So in this diagram, we have a scenario where one of the regions is having a problem, in this case, EU West, and its traffic is rerouted to the other 2 regions. So this process is called a region failover. And when this happens, all the traffic, in this case for EU West, is rerouted, taken away. So all the routers in that region, in the failed region, will see a significant decrease in their incoming traffic. So when that happens, you may be tempted to scale all the routers down, but you shouldn't, because eventually, after the region recovers, traffic may be routed back, and then you'll have a flood of data to handle, and all your routers will have been scaled down. So then you'll have a lot of lag buildup across all your thousands of routers, and that could impact the Kafka clusters. Maybe they would become unhealthy, and then you'd have to request a bunch of containers all at once, which you could run into container allocation issues. So basically, you don't want to disable scale downs during, or you don't want to scale down routers during a region failover. You want to keep the routers provisioned, even though you don't have any traffic coming in, so that when traffic comes back, you'll be ready to handle it. And yeah, that pretty much covers auto scaling. If there's any time for any questions, I can answer them.
Yeah, I'm not sure, Timothy, if you can see the questions that have been asked in the Q&A channel, but if you want, I can read out some of the top rated ones, or top upvoted ones. The first one, I think it's like upvoted by time. So the earliest, highest upvoted one is how frequently do you evaluate scale up or down?
Once a minute.
Okay, cool. Next one is, do you consider the application's latency SLA versus the traffic prediction error? How aggressive do you try to reset the baseline of the traffic prediction?
Yeah, so yeah, we basically reset the baseline on the traffic prediction whenever we observe 3 outliers in a row. That's the current strategy. That usually doesn't happen unless we usually don't have to reset the baseline unless there's a sudden change, like a region failover. So a bunch of new traffic comes flooding in from the failed region, or the workload is just inherently spiky. Like some routers see a burst of traffic for a few hours and then all the traffic goes away. In practice, waiting to observe 3 outliers to reset the baseline works pretty well. We haven't seen any issues because of that. We've seen issues because of other things, but not because of that.
Excellent. Next question is two-part question. Is each router its own application cluster or some common session or clusters involved? And part 2 is, can you describe the steps in terms of how the auto-scaling happens once the autoscale initiates a scale-up action?
Yes, okay. So we run 1 router per cluster. We don't do a shared cluster model for any of our Flink jobs. It's 1 Flink job per cluster. So yeah, how does a scale-up action work? So when we initiate the scale-up, so we have a little optimization. We keep the job running, but we add the new nodes first. And those new task managers get added, but no task slots get assigned to them. After all the new nodes come up, then we do a stop with a save point. I believe it's called graceful stop. And then we restart the job from the save point, which is pretty quick because all the new nodes are already there. And yeah, those are the steps we take.
Thanks. Next question is, do you plan to do auto scaling on other Flink configs besides cluster size?
Yeah, so currently, no. We essentially leave like picking the number of CPUs, the total amount of memory, and network bandwidth to deployment time, and we just do horizontal scaling. Currently, horizontal scaling is working well with the routers. So we haven't seen any issues requiring like vertical scaling yet. But if there's a use case that requires it, we'll think about handling it then.
Okay, next one, thank you. Next one is, given the recovery time, do you have requests from users to reduce the number of scale operations per day, especially for scale down, which is only good for cost, but no impact on the service itself?
Yeah, so some routers are sensitive because of what the user is doing, like stopping the job even for a short period of time, they notice it. So in general, when that happens, we don't have any special policy. We just over provision the job and disable auto scaling for those use cases that are very sensitive. But in practice, the number of use cases that we've seen that are highly sensitive to it are very few. Like out of the several thousand routers, we have maybe like a dozen or 2 dozen that have auto scaling disabled for that reason.
Thank you. I see we're at 6:45. So Timothy, I don't know if you're able to answer more of these questions just in the Q&A tool, but if you can, that would be great. But I think at this point, maybe I should turn it over to Gary to introduce our next presentation. Timothy, thank you very much for that presentation.
Thank you.
Yeah, thank you, DJ. Thank you, Timothy. Hi, all. I'm Gary. I'm a senior manager in LinkedIn's stream processing team. It's my pleasure to introduce Aniket Mokashi from Meta. I actually had the privilege of working with Aniket on Facebook's stream processing system in the past. So Aniket is currently an engineering manager on stream processing team at Meta. He has contributed to the development of large-scale data processing frameworks and platforms in the past. Before Facebook, he worked in YouTube, Twitter, and Netlfix. Also a committer and PMC member on Apache Parquet and Apache Pig projects. Okay, so Aniket, passing the floor to you.
Okay, I was muted. Hey, thanks, Gary. Thanks for the introduction. And I'll first say that, hey, also thanks to Timothy. I think really nice talk, very technical and insightful. I think I learned quite a bit from that talk. It's going to be hard to top that one, but I'll give it a try. So with that, let me start presenting what I have to talk about. So yeah, like Gary mentioned, my name is Aniket Mukashi. I'm an engineering manager on real-time data team at Meta. I'm going to talk about stream processing platform called XStream that we have built at Meta. This is like a planetary scale, fully managed stream processing platform. I think we've talked about XStream in a couple of forums over the last 2 years. I think I gave one talk about it at Flink Forward Global last year, and Varen from my team also talked about it in the Data at Scale conference earlier this year. So if you've seen those talks, I think this would be quite similar. But I think the one difference is that this is a live talk, so I'm hoping I can take a few questions and kind of throw more light on XStream if people are interested in knowing more. Also, like Gary mentioned, he has been partner in crime with me in building XStream. So I'm also hoping that Gary can help me answer some of the questions as the talk proceeds.
I'll try my best.
Yes,
okay.
I would appreciate that. And with that, I'll get started. I think I have 3 kind of topics that I'll try to cover. First, I'll give you a high-level overview of real-time data at Meta, like how our data flows through our streaming systems. Then briefly mention the evolution of the stream processing ecosystem. This will give you a perspective on like where we started and how we got kind of here. And then lastly, I'll cover XStream's architecture, its design principles, and so on, and get into details of how XStream is built. So with that, let me get started with the real-time data at Meta. So this is like a very typical diagram that you would see in any stream processing system, like all the basically devices, web tier services, they produce a lot of logging data. So similar to every other place, we have a logger library in multiple languages that basically produce logging data, and that's stored in our messaging pipe called Scribe. Scribe is, I think, also an open source project that was, I think, built at Facebook about 10 plus years ago. But since then, it has evolved into a lot of things. I think the open source version is quite different than what we use internally. But this is our main kind of messaging pipe. It holds a lot of data. And then from there, the stream processing pipelines read data primarily from Scribe. They also read from a few other sources, but majority it's from Scribe. They process them, and then that data goes either back into Scribe or goes into our warehouse or goes into other kind of feature stores or other storage systems that we have. So very typical, nothing kind of interesting here, but good kind of summary of how data is doing overall. And then overall, we have like 3 kinds of use cases. There is streaming analytics. All the time series analytics that you need to see, windowed aggregations for either debugging some application or debugging your performance or looking at your experiments, or real-time dashboards for like monitoring your applications. So we have a time series database called Scuba. So a lot of streaming analytics output goes into Scuba so that we can real-time kind of do monitoring on our applications. Also real-time metrics, so custom metrics that people want to kind of get notified or alarmed on based on some anomaly detection and so on. So that's one kind of use case. Second we have is streaming transformations. So as kind of streaming data arrives, you want to join it with some dimensions, like enrich the data, clean it, organize it, transform it. So all of that also happens on is one of the use cases. And then these basically use common built-in operators to do transformation, aggregations, filtering, and so on. And last but not least is real-time AI and ML. So these basically, there are various kind of stages of life cycle of AI ML that use stream processing. I'll try to cover some of that in the subsequent slides. But you can think of like it enables predictive analytics, especially in real time, fraud detection, and all those kinds of use cases. So with that, yeah, let me talk about this ML space a little bit more. There are a few examples I can try to talk about. So, for example, real-time ML gets used in recommendations. So, we're trying to figure out what kind of short-form videos or stories that our users would be interested in. So all that kind of use case gets powered by real-time machine learning. Content understanding, so what topic or topic is the video or news about, like all the content on our platform, what is it about, extracting that in real time so that we can take actions on it. Then that's the third, I think, fraud detection or abuse. So figuring out what type of content on our platform is legit versus how much is fraud or kind of bot generated. So that's one of the use cases. And then system monitoring. So like I mentioned before, like all of our system kind of checks are automated with anomaly detection and everything. So that all that is driven by the real-time data. Next, then let's look at like the role of real-time data in machine learning. So a typical like machine learning application has like couple of parts. Like one, you have to do feature engineering or feature extraction, and then you rank those features based on kind of some model that you have in mind, and then you use those features to train your model and refine it and keep refining over time. So the feature extraction typically needs something like a filter project, some way of enriching your features, using aggregation kind of to again make the raw events into actual features. And then those features then get stored into some kind of scalable feature store, which then is used in model prediction, model building. Then that model predictions are used are served back to the user, and based on that, user take again actions, which is used to kind of train the labels and again kind of feedback into the system. So this is a typical system, but amongst all the kind of components of this system, you can see that like half of them are powered by real-time stream processing. So you can see how much kind of use of stream processing is there in machine learning, especially at Meta. So again, diving deeper into just pure feature engineering, one thing we have at Meta is this feature extraction platform. So we provide like a DSL for engineers to kind of engineers or analysts to express their feature logic into a high-level DSL called feature definition. And then from that feature definition, which is not just a very high-level language, but it also allows to write functions and UDFs so that they can do more complex feature extraction from the raw data. But that feature logic or DSL gets compiled into like SQL queries at the end using this feature compiler. And these then queries can be run on, can be deployed on the XStream platform or stream processing platform. So that way, the feature engineering is very transparent to the end users. They just basically express their logic, and then we take care of all the feature extraction, storing that into the right output data output stores, and then keep running this, so maintain all the life cycle of that. So this is where the fully managed part comes in, and I'll cover some of that when I talk about XStream as a platform. So moving on, before I kind of talk about XStream, let me very briefly cover, like in 2 slides, cover the journey we have had so far. Just to give you a perspective on how we got here, why we built XStream in the way we have built it. So yeah, this is a brief or timeline on how things have been at Meta or Facebook. So 10 years ago, this is before we even had a system called Stylus. People were basically building their own kind of services to process streaming data. Like as the logs data arrive, you basically write your own microservices or any kind of services to process it. Over time, we realized that, hey, all these kind of streaming applications require a standard set of library to basically express your filters, manage threading, manage your IO on a separate thread pool, all those good things. And that's how Stylus was born. So Stylus is basically a library for, it's a very low level library for any application that wants to write a streaming job or a streaming kind of express streaming kind of functionality. They use Stylus as a C++ library. So this is currently embedded in like just streaming platform applications as well as like normal applications across Facebook. And then along the way, we saw the need of being able to do streaming analytics in streaming analytics for kind of generating features or just purely monitoring purposes. And that's where Puma was born. So Puma is kind of a Java-based analytical engine we built around 2016. And that basically people, like, it is again a fully managed platform. You type in your streaming SQL and just plug it in, and it keeps running and keeps producing or powering your dashboards. So this came along around 2016, and then later in 2017, people saw a need of like building some kind of a hosting solution for Stylus applications, because Puma was only specific to analytical use cases or SQL-based use cases. But we also saw a need of custom C++ applications and making them kind of fully managed at Meta. So for this, Turbine was born, and Turbine is essentially like a containerization solution similar to how Kubernetes is, but it's very specialized for streaming kind of use cases. And then right after that, then around 2018-19 time frame, we realized that the ecosystem has really kind of split into a lot of pieces, and then we really need one platform to rule it all. Like we needed one platform to consolidate all of this, get the best pieces, best ideas from all the systems into one. And that's where around 2021, we built XStream for all of the customers at Meta. So moving on. Yeah, so like I said, this is from a paper we published around 2016-17 timeframe. It kind of gives you a sense of, it's called real-time data processing at Facebook. It gives you a sense of all the various tools and systems that that were there as part of the ecosystem. So we had Scribe, which is still there. We had Puma, which was a fully managed stream processing service for like writing your SQL queries, and the system itself was built in Java. Then we had another system, Swift, for people to write their applications in Python. This was just to do very quick analysis of your streams, like filtering and just monitoring purposes. Then we had Stylus to low-level stream processing framework. Then Laser to do like a remote lookup joins on top of Rocks, like a distributed Rocks DB. And then Scuba, which is still there again to do slice and dice analysis on the or time series analytics on our data. So with this ecosystem, we realize like we have one kind of tool for every kind of language, and it's not an ideal situation because now we have to build expertise in all these 3 languages. As a stream processing team now, really have to manage all these all the complexity around all these languages, and if you have to do privacy or security, like you have to do it those many multiple times. Also, our users are not very happy because now they have to choose between the tool to use based on what they're trying to do and get our recommendation for that and so on. So it wasn't very ideal situation. So that's why we decided to build XStream. And XStream was and then I'll cover its architecture and design principles. So to give you idea on how we kind of got rid of all the other things to build one streaming solution for everything. So why we built XStream? Like I was saying that we wanted to accelerate developer velocity. So we wanted our developers to just focus on writing the business logic and manage and let us manage everything else. So not worry about where to deploy their stylus code or how to deploy their Python Swift code. All of that, we wanted to take care of that, but to still give them enough flexibility to express any kind of complex business logic. And this was very important at Facebook Scale because we have our customer base is quite wide. We have a lot of developers. Then we also wanted to take on all the operational costs, because if you just build libraries, then people have to bear their own operational cost, and then most of the time just goes into keeping the lights on. So we wanted to take care of that. Also provide authoring ease. We did SQL dialect across all our batch interactives and streaming use cases, which is like Spark and Presto and XStream. So that was one of the choices we made. And as we made progress to this, we also wanted to move to C++ or something more advanced, so that we are more efficient. So achieve 2x more efficiency from the predecessors, even just plain C++ code. And then, like I mentioned, wanted to do fully managed service. So scaling or auto scaling, taking backups, catching like backfills or any kind of things are fully kind of managed and automated. So that way we can really scale to tens of thousands of applications running on our platform. So this is like a kind of a very high level architecture diagram for XStream. XStream, the way the authoring experience looks like today is like you write your streaming SQL or a kind of a binary that you want to run on the platform, and as long as you submit it, the managed platform takes care of provisioning it using these management workflows. So it has its own control plane that has these workflows running to create an app, update an app, stop it, pause it, all the good things. With that, it also comes with auto scaling feature, load balancing, and also has a feature where of root cause, like automated root causing. So it can correlate various metrics and say, hey, your job is lagging or failing because of X, Y, and Z reasons. Also route it to the right person, like right on call based on the root cause. If it is a user problem, it goes to the user. If it is the platform problem, then it comes to us. Also provides multi-regional, like all the disaster recovery, all the good stuff of any managed platform. And on the data plane side, it has a couple of components. One is it has an eval engine, which has two flavors. It can do code generation, or it can use vectorized interpretive engine. I'll cover some of those details in the later slides. It provides like stateful and stateless support with state stores and libraries to do various IOs. We can plug in multiple types of state stores, which are very important for some of these machine learning kind of use cases. And then it does support all the machine learning storage IOs and formats and other machine learning related eval engines. Also, we have a disaggregated streaming shuffle. We use some specialized systems at Meta to do streaming shuffles, which are highly efficient and effective. So before I go into more details of XStream, XStream was built on Stylus. This is another, like I mentioned, almost a decade-old library. But Stylus is really good at writing fault-tolerant, scalable stream processing applications, because it provides the basic building blocks of any streaming systems, which is like all the sources and sayings, the operators, the watermark, checkpointing, triggers, state backend. So basically all the necessary building block for any streaming application. It also kind of manages threading and coordination between various operators very nicely, has very well-known flags or well-documented flags to play with that. But the downside of this kind of just using this as a tool to build streaming applications is that it has steep learning curve. Like even though there is documentation and it does take a long time to understand all these concepts and ramp up on those. So it has high maintenance. So it has high maintenance and operational cost because as a library, the operation cost is still on the developers to kind of run stylus in their own systems. So that's why we decided to build XStream. When we decided to build it, we chose C++ as our language with stylus as the building block. So XStream at the very core is built on stylus. And then a couple of other design choices we made are we use Common SQL as or what we call Core SQL as a dialect. So we consolidate all the dialects at Meta to one dialect and build a SQL library for it. That's called Core SQL, and it's used across Spark, Presto, and XStream. So that helps us kind of really simplify or simplify a journey for kind of analytics for our users. Then we've chosen to do interpretive kind of engine approach over compile code generation approach, and we have built XStream on top of vlogs. Which is a vector, which is an open source project. There's a link down there, and it's a vectorized execution engine. We want other systems to also start using this. It's a very well-built library. So we encourage like people outside of Meta also to kind of use it in their own systems and products. And then why we chose C++ is C++ is very mature at Meta. I mean, it is definitely more performant than Java. Also, Java support is very limited at Meta because over the time as we built privacy aware and security aware infrastructure, the more investments have gone into C++ versus Java. Then many backend services, especially on the ML side, on the ads side, are written in C++. So migrating their logic into something Java specific is much harder, which is a problem we see when we onboard people on, for example, Spark or Presto, because they are Java-based systems. And then efficiency and performance are very important because at the scale that we run, the numbers really add up really quickly. So it is very important to pay attention to efficiency from the beginning. So a few comments on Core SQL. So Core SQL is this was an excellent choice for us because it standardizes like all the dialects across Meta. So the struggles our users had when they were kind of moving their like experimentation query from Presto to streaming, that really went down because of use of Core SQL. Also, our UDFs could standardize because you could use the same UDFs across all the engines, and that way you don't have to rewrite your UDFs. So and also their behavior remained the same across engines. So that portability was one of the important angles. Also, we plan to open source this. I think this is not yet open source, but we'll plan to open source this Core SQL library as well. And we will support streaming extensions as part of it. So all the standard windowing like tumbling windows, sliding windows, session windows will be supported on that when we open source it. Next, I'll talk about query execution a little bit. So back when the XStream was getting built, the first option we chose was doing code generation. So when you write your streaming SQL, we'll compile that down into C++ code. We'll code generate the C++ code and then compile that into a library or a binary to run. And that's how we deployed like really highly optimized code on our platform. But however, the problem with this approach we soon realized was we had to build one binary per pipeline. So which means there was a proliferation of binaries that we need to support. which became a problem by itself, because now all the tasks have to download those binaries, and the binary even on the customer side, building the binary was a painful process, because if I had changed one line of code, I have to now wait 30 minutes to get my binary out and test it out and so on. Then it was really hard to scale operationally because of the download problems and other things I mentioned, which caused the reliability concern. So with that, I think in the next iteration of XStream, we decided to do the interpretive approach. So with interpretive, what we do is instead of generating code, we actually generate it's typical to any kind of query engine, just generate a physical plan, and then use that physical plan to drive the computation, even the streaming computation. So this basically planner generates a distributed execution plan, and then the C++ worker just interpret the plan and run it locally. And then so because of this, the compilation, the whole end-to-end flow of end-to-end iteration speed really increased, like became order of seconds or minutes, because there was no build process needed. All you do is submit your query to a query planner and get your application deployed. And then also, which meant was there is a single binary for all the applications. So problems of bugs or any kind of robustness of the binary itself was much higher, and it was also easy to scale operationally. And other kind of other things we did to make this interpretive approach even more effective was we started using vectorized execution, so leveraging SIMD instructions and vectors more in our kind of interpretation code. So as I mentioned, when we use vectorized execution, we use this commonly built library at centrally built library at Velox. The Velox library is one of the things we are trying to do at Meta is use this library across all our query engines. So Presto, Spark, and XStream, all three are unified. All three engines are unifying with Velox. So with that, I think we get a bunch of benefits of efficiency, consistency, reusability. So it's all win-win for us. The right side here, I show like a graph of how we basically structure our code in terms of how to build an evaluation engine from Velox. So at the bottom, we use this vectorized library, so everything is expressed, all the data is expressed as vectors, and then from there we build expression evaluation functions for filtering and so on, and then build operators on top, and then orchestrate through that through a task and a driver. So Velox is an open source project. You're welcome to take a look at our project. It's quite popular at this point. So just to summarize again, this is the final kind of high-level picture of XStream, that we start with core SQL, which basically generates a logical or physical plan, and then that plan gets deployed on individual nodes with Stylus framework running at the bottom with XStream query runtime actually interpreting that query plan and running it. And that runtime essentially uses Velox vectors and expressions to process the data. So how did that compare with what we had before? So just by Velox, moving to Velox from Java, we see 2 to 10x performance, and these are numbers we have got from just Presto. Changing Presto's engine from Java-based engine to Velox engine, we get about 2 to 10x. And from stream processing, we have seen we've migrated a lot of our Java Puma-based applications to XStream, and that has shown clear wins about 2 to 10x again in terms of CPU savings or total cost savings. So it has been a clear win from C++ to Java. And even just from code gen versus interpretive, we have seen a lot of improvements just by using this vectorized engine. So we just see like with the hundreds events of like batching 100-ish events, the compilation we can save up to 10 to 30% memory, and then just during catch up of a lag, we can easily see the throughput increase by 30 to 50%. With the same CPU and even slightly less memory. So overall, this kind of architecture has given us a lot of benefit and edge over kind of previous architectures we have had. So with that, I conclude my talk. So thank you. And if you are interested in knowing more, definitely feel free to drop me a note on my email or on LinkedIn. If you want to get involved with vlogs, I would really welcome it. With that, I open the floor for questions, if there are any.
Yeah, thank you very much. So there are a few questions the audience has submitted. I'll just go through them. Okay, so in XStream, so we provide both declarative and imperative. Do they interact? Can they mix?
Oh, that's a good question. We don't allow this yet. It would be an interesting project to build, but as of now, the SQL world is declarative world is separate from the imperative world. You can definitely use the UDFs or common C++ code that you built across those two, but right now there is no kind of going back and forth like you can say like data frames or something.
Okay. All right. So next question is. Let's see. So I'm going through. Next one is in XStream, any thoughts of using Go or Rust in new infra initiatives?
I think our C++ ecosystem is quite robust, and for the users, they even want like more higher level primitives to work with, so that way they don't have to really deal with any of these the programming details. So I at least haven't seen much of demand for these newer languages.
Yeah, in my experience in Facebook, Go and Rust they do exist in limited pockets, but they are not widely used because of the tooling support in general, as Anik is mentioning. Okay, so
and
next
also I'll
one.
quickly say that a lot of data side of world is very sensitive to privacy security requirements for obvious reasons, and so it is very critical for us to use like a very well supported language. So that's why we don't have a demand for this kind of newer languages.
Actually, that might be a separate interesting topic, is how the whole privacy and stuff is managed. That is a pretty significant effort in Facebook. Okay. All right. Next one is, what do you mean by using Velox in Spark? Do you replace the Spark SQL engine with Velox somehow?
Yes. So so we use kind of separate workers in Spark to use Velox. It's an ongoing effort. We have experimented with several approach, but we take a different approach from how what others have done. We right now use like a special sidecar process to run Velox engines. So Spark still remains as a execution kind of orchestration part, but we replace the actual engine, SQL engine with Velox.
Interesting stuff. Okay. All right. So next one, could you also talk about the execution engine once the logical plan is available via XStream, and how is it being scaled? Pretty big question.
Yeah. So I think scaling wise is actually a better story because with interpretive we are already using the same binary everywhere. So all you have to do, like all the task manager has to provision is the execution plan, and then the scaling becomes even more easier with that, at least on the data plane side. I don't know if that answers the question, but I think this is a very wide question. So
Yeah, so that this question is pretty broad, but in general, the execution engine is somewhat similar, where a pipeline gets materialized into many processes, right? Many C group processes, and then each of them gets scaled across the entire fleet. I think sometimes across regions too. So that itself is also a pretty interesting topic. Okay, cool. Thank you very much, Aniket. This is a pretty good overview of what Facebook is doing on its managed stream processing platform. Okay, so let me now, yeah, thank you. So let me now introduce Yanan and David from LinkedIn. So this will be for our third talk to talk about power machine learning feature engineering with managed Beam platform at LinkedIn. So Yanan and I are both in the stream processing team in LinkedIn. Yanan is a staff engineer. She has been working on the workflow API for authoring managed Beam applications. Prior to joining stream processing space, she has 3 years of experience in LinkedIn machine learning infrastructure. David is an engineer from LinkedIn machine learning infrastructure team. He has been working on building the FedEx real-time framework in collaboration on top of stream processing infrastructure. So thank you guys. So the floor is yours.
Thank Gary for introducing me and Yanan. Thank everyone to attend the meetup. We will provide an introduction about how LinkedIn powers machine learning feature engineering with a managed Beam platform. Here is our agenda today. And first, I will provide the motivation for real-time feature engineering. And secondly, I will introduce a nearline feature generation framework, FedEx real-time. And then Yanan will give an introduction about the underlying stream processing platform, managed Beam. And then the remaining time will be used for a Q&A. Let's move to the motivation part. And machine learning models are applied in almost all the key products like job recommendation, search, feed, and ads in LinkedIn, and powered by thousands of features about entities like companies and job posting and LinkedIn members from the economic graph. And preparing and managing features has been one of the most time-consuming parts of operating machine learning application and skill. There is a growing demand for fresh real-time feature data, and which are expected to have significant business impact by boosting machine learning models' relevancy performance. However, the gap existed for the feature freshness requirement and the original offline feature generation framework. And most our recommender systems relies on batch jobs that usually run once a day on offline activity data of members. This results in a 24 to 48 hours delay and between when a member takes an action and when that action has an impact on the recommendations for that member. And this results in missed opportunities. Real-time features can reduce the delay from 24 to 48 hours to seconds level, which can significantly boost the LinkedIn members' experience. Member will receive adopted fresh recommendation in seconds level. Before building a real-time feature generation framework to boost feature freshness, we build a proof of concept to approve the business impact of real-time features. We have observed a significant increasing and in business metrics across key products, including feed, search, job, and ads. Let's see a demo about how the real-time features boost the LinkedIn members' experience in job recommendation within seconds. Here is a demo video. Let's go to the job recommendation page. We can see a list of recommendations for engineering jobs. Then we search for principal data scientist job in United States. And then we can see the jobs recommended. And then we save some of them and the CSAI one. Then we select the Walmart one. Then we select the okay, so then we select the Amazon one. The next we select the Microsoft one. This tells the job recommender that I prefer the scientist job and at least in the short terms. Now I go back to the job recommendation page. We can see some data scientist job recommendations and within seconds. We don't need to wait 24 to 48 hours. Yeah, so with a significant business impact introduced by real-time features, the next question is how to scale real-time feature generation in framework level. The main stakeholders for feature generation in LinkedIn are AI engineers. There are multiple technological challenge for AI engineers when they build a scalable real-time feature generation application. Usually, AI engineers have limited infra knowledge. They have to integrate lots of streaming tools and infra and frameworks, including Kafka, Samza, and Beam, key value stores like Venice, and they usually have to write thousands of lines of code. And developing cycles usually cost 1 to 2 months. After the application deployed, the AI engineer have to configure the operational metrics for monitoring the jobs. So an effective real-time framework with user-friendly interface is required to scale the development and operation of real-time features with high productivities. Based on the above pain points for AI engineers, we propose FedEx real-time to authorize real-time feature definitions. Underlying it and manage Beam and the streaming processing infra is built to handle deployment and operation and runtime. Now, let's introduce FedEx real-time first. FedEx real-time and the nearline feature generation platform is services to quickly generate real-time feature data and store them in online stores and make them available to AI models for consumption. The objective is to improve freshness of member activity data from days to seconds to enable adoption of LinkedIn members' experience in real time. The reason why we are doing this, because improved data freshness drives improved prediction and leads to business impact. FedEx real-time is aimed to give AI engineers an easy way to quickly create real-time features. Here is a high-level architecture. From the AI engineer's perspective, the real-time feature generation is a 3-step process. First, authorize the real-time feature definition. Then build the definition into managed Beam job artifacts. And finally, deploy the job. After that, the job will be kicked off on managed Beam platform, and streaming infra team will manage the job for any platform-related operation. User code has no dependency on runtime infra. In this case, the runtime infra is split from the feature definition, and user code AI engineers can focus on the defining features, and which is the domain they are familiar with, without the need to know the underlying runtime infra, and which is the domain they are struggling with. Therefore, the development and operation of real-time features is scaled with high productivities by FedEx real-time and managed Beam. Let me provide an example how to use FedEx authorize of real-time feature generation pipeline. FedEx real-time provides the feature definition authorizing interface based on the customized Python DSL, which transforms workflow nodes for streaming data pipeline into a chain of Python operators. In this example, it shows the real-time features pipeline for feed image embedding use case. It is intended to capture the image captioning information and the embedding features from the image uploaded by linking members. And the first DSL operator read is used to retrieve the on-site update events triggered by uploaded image in real time. Then a select operator is used to retrieve the on-site ID used for the image captioning model inference. And then the MAMP model inference operator will apply the image captioning model config used for inference. Then the write operators will be applied to store the resulted embedding features from model inference into key value store. And this simplified authorizing process reduces the developing time from 1 to 2 months into a couple hours. And in code levels, thousands of lines of code are shrinked into tens of lines. This is pretty productive for AI engineers. I will hand over the following section to Yanan to see what happens in infra level after the real-time feature definition are authorized by engineer.
Thanks, David. So now that you understand why we want to support real-time features, what FedEx real-time is, and why we want to run it on a managed platform, I will give you an introduction of the managed Beam platform we are building here at LinkedIn and how it has made the life easier for those FedEx real-time pipeline owners. First of all, I want to echo back on the motivation, why we want to build a managed platform and what are the problems we're trying to tackle. So the difficulties David described in building and operating nearline applications do not only exist for machine learning engineers. These are also typical problems that we observe for all of our users. Basically, we see users need to have a good amount of infra knowledge and do extensive coding in low-level API in order to author a nearline application. And users need to manually set the job, which they often find hard to do. And when there's a job failure, it's hard for them to diagnose the root cause, whether it's a system error, a user error, or just a performance issue. And all this user pain eventually leads to pain on us, the infra team. We find it takes a long process to roll out system upgrades and fixes. The more complicated the application is, the longer time the process takes. And users missizing the job often ends up with inefficient usage of resources. And our team constantly faces heavy on-call load with a large portion attributes to operation issues. So all these problems motivates us to build a managed Beam, a platform to remediate all this pain in building and operating stream processing applications. So we understand the problems. The next is to build the solutions. We try to tackle problems that's reviewed in all the stages of a nearline applications lifecycle, from authoring to deployment and then operation. Our goal is to simplify the authoring and the deployment process and to manage the operation of nearline applications for the users. Let's start with, let's talk about the work we've done on the authoring side first. To simplify the authoring experience, we introduced a concept called workflow components. So workflow components is a higher level of abstraction we build on top of Beam SDK. One workflow component is a reusable subdag for a common operation. For example, our team offers a list of standard components that can be applicable for all nearline applications, like a source, sink, filter, projection component, a table drawing component, and a window aggregation component. We also allow partner teams to define their own domain-specific components that are reusable for applications in a specific domain. For example, for machine learning applications, there always need a machine inference machine inference component that execute a model for predictions. And we also have feature fetcher component that can read predefined features from LinkedIn's virtual feature store. A key feature of workflow components is that every workflow component exposes a protobuf API. So what it means is that the interface of the workflow component is defined as a protobuf message. Here are some examples. On the left, we have a source component that takes in definition of a stream, which tells the source component where to read the data from. And we have a sync component that can either take in a definition of a data table or a definition of a stream, which tells the sync component where to write the data to. On the right side, we also have example of a projection component and an inference component. So with the protobuf API, we can have the users to construct a pipeline as a protobuf DAG without having to bind to any platform binaries. I will explain further what that means. So here is the example that David just showed. It is a FedEx real-time job authored in FedEx real-time DSL. It reads a Kafka message, select some field, do a model inference, and then write the output to a data store. So every operator here has a corresponding workflow component. During build time, the compiler will take the workflow component protobuf API to translate this piece of DSL into a pipeline DAG in protobuf, with each node being a workflow component. So here is a graphical view of the generated protobuf file. You can see it's a simple DAG constructed from the source component, the projection component, inference component, and the sync component. So with protobuf API, we can have the user pipeline represented in protobuf so that it can stay language neutral and runtime agnostic, which means we can switch the implementation of workflow components from Java to Python, or switch the runtime engine from Samza to Flink without affecting the user. And one more advantage is that because the generated pipeline proto does not bind to any platform binaries, it allows us to independently deploy platform code from user pipeline, which is a capability we call split deployment. So now that we know how to author a managed Beam job, let's talk about the deployment. As I just explained, split deployment is a capability to independently deploy platform code and user code. This diagram demonstrates how it works underlying. So on the left side, we have a code repository for the workflow components. And during build time, it can package all the platform jars into a platform artifact. And we also have a code repository for the user job. And during build time, it packages the generated pipeline proto into a user artifact. Both artifacts will be uploaded to Artifactory. And during job deployment time, the two set of artifacts will be downloaded. And the pipeline proto will be converted to a real Beam pipeline and gets executed on the Samza runner. So with the capability to split deploy platform code and the user code, we can roll out platform bug fixes and upgrades or new features in a much faster pace without having to wait for users to pick up the latest dependency in their own code repository. And even though many simple use cases can be constructed, many simple pipelines can be constructed from workflow components we offered, there are always more complicated use cases that requires user-defined code, which is much harder to manage because it can be any arbitrary code. So to solve this problem, we introduced a multi-process framework to isolate the execution of user-defined function and platform-defined function. So say if we have a pipeline that is constructed from components that is purely platform-defined and the components that uses some user-defined code, and then during job launch time, the PDF components will be assigned to a PDF worker process for execution, and the UDF components will be dispatched to a UDF worker process for execution. So being able to separate the execution for user-defined functions and platform-defined functions is very important for us to achieve performance and fault isolation, which makes the pipeline much easier to manage. So after the job is deployed, we want to know how to operate the job. So firstly, after a job is successfully deployed, users can go to a GUI dashboard to check out the job status, go through the basic information of it, check out the applied configs, and they can even check out the logs on the GUI dashboard. We certainly don't expect users to constantly monitor the dashboard, so we automatically generate a set of metrics that are crucial to monitor, and alerts will be automatically sent to both the pipeline owner and the platform team if any metrics indicates that the job may not be healthy. So a very common issue we've seen is that the job may run out of memory or CPU, and which causes the processing time to delay and eventually cause a huge lagging. And in the past, this kind of issue always requires manual intervention. But on Managed Beam platform, we introduced the capability of auto-sizing, which can automatically size the job's resources, including memory, CPU, and parallelism parameters like thread counts, container counts. So pipeline owners can check out the operations that has done by the platform to automatically scale up and scale down the job on the GUI dashboard. So we know how we have built the solutions. Let's summarize the achievements we have made here. So firstly, we make it easier to construct a pipeline through the workflow component API. We have added the capability to deploy and execute the platform code and user code independently. And we added made it easier to operate Managed Beam jobs with the capability of automatic stop sizing and easier monitoring and alerting. Here are a list of improvements we want to work on in the future. We want to be able to separate the platform log and the platform code log and the user code log. We want to build a centralized and queryable logging system for user to easily query the log without having to look at a single log file. We also want to add the capability to do automatically error detection, triaging, and remediation. That's what we have for today. We are happy to take questions.
Looks like David has been doing a good job answering questions.
Okay.
So thank you. Let's see, any other questions here? I think they are all being answered.
I think there is a follow-up question. Okay, yeah, I think Bing Feng answered.
Cool. Okay, so I think these are the 3 talks we have for this evening. Thank you to all the speakers. They're super interesting. Please feel free to reach out, connect on LinkedIn. And we have a upcoming meetup in October as well. So you are very welcome to share your ideas and your projects in this forum. Just reach out to me, David, and Effie. With that, we can conclude today's meetup.